Okay, and now it is my pleasure to introduce to you Eric Blossom. Eric Blossom is the originator of the GNU Radio project, which is a real-time signal processing framework. And he will now talk to us about how you do radar with low-cost tools and free software. Welcome, Eric.
Very good, thank you. Hi, everyone. It's really great to be here. And I want to do, before we kind of really dive into the radar part, I want to give at least a couple minutes on GNU Radio. I've done that kind of talk a bunch, but I'm not sure who's seen it. So GNU Radio is fundamentally a free software toolkit for building real-time signal processing systems. And generally speaking, what we use it for is doing radios. That's just because it's our personal interest, but we've got other people who are using it for radio astronomy. There's people doing like atomic force microscopes using GNU Radio as the control loop for those. It's a pretty good sized chunk of code. It's about 250,000 lines of code. It's in C++ and Python, and it's fun to play with. So kind of heading down the private investigations thought we were interested in, well, what's really flying around out there? Where are the black helicopters and are they coming? There are also people who do all kinds of different stuff with radar. So I just want to get going here and see, we'll kind of cover radar, a little overview of radar in general, and then the kind that we're building, and then we'll show you what we got working. So to start with in radar, it's been around for quite a while. It's an acronym that stands for radio detection and ranging. But in these days, it's more than where they mean ranging is distance. Really, at this point in the game, people really want to know where stuff is. And pretty much how it goes is, I don't know how it is here in Europe, but in the US, years ago, before digital TVs came out, that you could be watching your television and an airplane would fly over and the picture would get all wiggly. And then it would get back good again. Does anyone have that experience? Yeah, okay, good. So anyway, we would call that like multipath, or this idea that there's like a signal coming the direct path to your television, and then it's also one is coming up and bouncing off of the airplane and then back down. So what radar is really all about is watching the stuff bouncing off of things. And the things you could be bouncing off of could be people walking on the ground, they could be cars, they could be airplanes, they could actually be satellites. People use radar to watch where satellites are. Lots of good stuff. So, and depending on the kind of radar system you build, there's a bunch of stuff you could figure out. And you get some of these or all of these depending on what you're doing. So how far away it is. This was the real first use of radar. They basically would send a ping out and they measure how long it takes to come back. And that gets you how far away. You can also figure out how quickly it's moving towards you or away from you. This is because of the Doppler shift. Like if you're watching you're at a racetrack and you have like Formula One racing and the cars are going right on down the straightaway. You hear the engine, the pitch of the cars comes up and then descends as they go by. That's the Doppler shift. So it turns out it works with radio waves also, not just sound. Bearing, kind of the direction of the object. If you think about typical airport surveillance radar, they have a thing that spins around. So they get the bearing by kind of mechanically knowing, well, I had my antenna pointed over that way. And then some of the kind of bleeding edge stuff that is very popular in certain areas is this idea that I should be able to tell actually what kind of an object it is. And they can do things like this. There's some really fancy stuff they're doing in kind of the money is no object department here. They can kind of figure out what stuff is by watching the radar cross-section. They can watch how the radar cross-section changes over time. They do like these synthetic aperture radar where they get like a two-dimensional image, and again they're doing like fast Fourier transforms in 2 dimensions, and then they map it up against some other thing and they go, it must be such and such a kind of airplane. There's other cool stuff, just in the other cool stuff you can do with radar, is that when you look at airplanes, it turns out that, for example, if you're looking at propeller-driven airplanes, you can actually tell that it has propellers, because in fact the rotating blades show up as sidebands in the radar return signal. And same thing with jet engines, believe it or not, is that because if you have an angle where you can see the turbine spinning, you can say, oh, it must be spinning this fast or it's got this many blades. Helicopters, of course, are the same kind of a deal. So there's a bunch of kind of interesting stuff that shows up. All right, radar's been around for quite a while. Christian Helmsmeyer is the first one that I know about, spark gap transmitter, and he was detecting ships. These guys, the next people is Holt and Young. These guys were at the US Naval Lab. They were actually doing propagation experiments with HF radio into the ionosphere, and they had antennas aimed up. And all of a sudden they noticed, we're seeing like the wooden boat that's in the river over there causing a problem. They're going, oh, wow, look at that. And then in the UK, 1935, they actually set out and said, yes, we think can detect aircraft, and they ran an experiment and could do it. The stuff really heated up in World War II, kind of like all sides in that were building radar systems or attacking other people's radar systems, and it got, that's kind of where it really geared up. Okay, this is kind of your typical kind of radar thing you'd see at the airport. It's going to be spinning around. This is really the part that we think of as the radar. This is actually just a big reflector. It's the dish, and it's not in this image, but out here somewhere off the right-hand side is the feed horn, where they're actually transmitting the signal in and listening out. How these things work is they send a pulse out. So the transmitter runs for a little bit, and then it stops, and then it listens, and then it sends another pulse out, and then it listens. So it's basically a pulse-based radar system, and the transmitter and the receiver are at the same location. So you run one, and then you listen, and there's all this fancy stuff about how you design, what kind of signals you send, and how wide a frequency they are, and how they're modulated, and how frequently the pulses go out. I mean, you start thinking about if you send these little pulses out, there's this ambiguity. If the pulses are closer together than how far away stuff, all of a sudden you can't tell if it's far or close. This is another kind of mainstream radar. This is, in one sense, this is the PAVE-PAWS system. This operates in the 400 megahertz band. Each of these big panels, this thing's about 100 feet tall, probably, so 30 meters probably tall. Each of these big panels has about 3,000 separate antennas with transmitters and receivers behind them, and each element is about 300 watts. This thing and basically by changing why they're called phased arrays is because changing the phase, basically timing an angle of what you send to each element, you can steer the beam around. So even though there's no mechanical moving, this actually beam, they can sweep it around. There's two of these that I know of in the US, one's on the East Coast and one's on the West Coast. This has a lot in common with the other one we just looked at, which is the transmitter and the receiver are in the same place. So this thing does the same kind of trick where it transmits, and then it waits, and then it listens, and then it goes and it transmits again. Okay, here's another one. So this is your basic, radar gun or whatever. This one typically operates at about 10 gigahertz. Same basic idea, that it's a pulse-based radar system. The transmitter and the receiver are in the same place. They run the transmitter for a little bit, they listen, and they're basically measuring. In this case, they're measuring Doppler. It's like they're bouncing it off your car, and they want to know, is it coming towards them or going away from them? All right, the radar systems we just talked about, all three of those are what we call monostatic radar systems. Those are kind of the traditional ones. That's where the transmitter and the receiver are located at the same place. Another interesting class, and it's the one that we'll be using here, are called bistatic. And this is a situation where you have the transmitter and the receiver are not in the same place. They could be separated by tens of kilometers or hundreds of kilometers. It just depends on how the system's put together. The final category, which I'm not going to talk about except just to mention it here, is the case they call multistatic. And this is a case where you have multiple transmitters, multiple receivers. They're networked together, and they kind of all figure out by watching everything together and kind of doing the sensor fusion thing about what's going on. So the bistatic case, transmitter receiver are in different places. And where this came from originally was, you know about anti-radiation missiles? These are the ones that they have on airplanes, for example, and they watch somebody turn on their little radar system on the ground, and then they just go, fire the missile and have it home in on the radar system. So that was the initial thing about maybe we should put the transmitter and the receiver in two different places. The other reason that they use this is this remote target illumination. This is more of a This is an exercise in engineering, because what you have in this situation is typically there's some aircraft flying around, like say an AWACS, that has a great big antenna on it that has the transmitter and shines down on the target on the ground. And then a missile is launched, but the missile, because it's physically very small, has a very small antenna on it, which means it doesn't have much gain. So what they get in this case is they can have this big transmitter antenna, which can send a lot of power, and a small antenna on the missile or whatever, and it all works out. I guess that's what they call it. Okay, here's the basic diagram on bistatic radar, and we'll see in a minute why we like this. So we've got this, at the bottom of the screen here, we've got this visible up there, let's see. Okay, so we got the transmitter, and we have the receiver. Now, all that we require in our case is that we know we know the relationship between the transmitter and the receiver. So we know, kind of arbitrarily, we could say, well, they're on the horizontal line, and we know how far apart they are. Then we've got this target or targets up here. And so what happens is the receiver sees two signals. It sees the direct path comes off the transmitter, like the short way. And then also there's this other path, what they're calling the illumination path over here. So it's basically the signal goes off of here, bounces off my target, and comes back here. So if you start thinking about, well, what can I do with this? If you can think about, like, you've had this pulse, you could measure, like, the leading edge of the pulse, and you would see the pulse come twice. You'd see it come once really loud, just kaboom. That's the direct path. And then you see a delayed version of it that comes sometime later. And how much later it is basically the difference in these two path lengths. So you've got the short path, L, and then you have the long path, RT plus RR. So basically, you know the speed of light, and you know this difference in time. So this starts to give you how you can begin to put the solution together. It turns out knowing just the time of arrival is, between the two pulses is not actually enough to physically place the thing. Because if you start thinking about back to some analytic geometry, that describes a hyperbola. So there's a whole family of places that target could be for any given shot where it is. And it turns out that if you just take multiple collections or you throw in also information about its velocity, you can start figuring out actually where it really is. The other thing to notice is we will talk about the distance, where within the monostatic radar case, since the transmitter and the receiver are in the same place, you send this pulse, it goes out, hits the target, and comes back in. And if you just measured that time of transition, that's really like it goes out and back, so it's twice the distance, and you know the path out is the same length as the path back. In the bistatic case, they're potentially different lengths. So you get this idea of distance, but it's not just one way. Likewise, when you look at the Doppler shift that you get in a situation like this, it's the change, you know, normally this Doppler, you think about it's the change in the path length. Well, in fact, it's still caused by the rate of change of the total path length. But again, you don't know if like the RT path is shortening or lengthening or the RR path is shortening or lengthening. So it's a little more complicated math than in the monostatic case. The other thing, kind of one of the basic rules of thumb is if you're working your math here, and if you shrink that baseline L down to 0, it all ought to work out just like the monostatic case, where they're both in the same place, and if they're not, then you're, you know, oops, you don't have it right. Questions so far? All right, and then to make things more interesting, in the general case, everything is moving. So you got the transmitter's moving, and the receiver may be moving, and the target may be moving. Again, all we require in this is we need to just know the relationship between the transmitter and the receiver. Examples where the transmitter and receiver are moving would be, for example, two aircraft, one of which is illuminating, one of which is watching. It could be the transmitter is a satellite and the receiver is an airplane. The target could be also moving. So what happens is kind of a sort of a footnote is they have this idea. People here have been on boats with radar systems and they have this like sea clutter where you get like the waves start showing up and you can turn the knob down.